Okay, so the last thing we're going to be able to get to, and there's so much more to learn in numerical analysis that we just don't have the time for in this class, is going to be eigenvalues and how to find the different eigenvalues of a matrix. Okay, so just for general definition, so here's the definition. So let's let A be an element of all the M by N matrices. Okay. Then lambda, which is a real number, is an eigenvalue of the matrix A if there exists a corresponding vector X that's an element of Rn. X cannot be the zero vector such that AX is equal to lambda X. Here, X is the eigenvector. Corresponding to lambda. Okay, so how do you find it? All right, so to find lambda and X, you solve AX is equal to lambda X. And so then you write AX minus lambda X is equal to the zero vector. And then you get AX minus lambda times the identity times X is equal to the zero vector. And then you get A minus lambda times the identity. That's a matrix times the vector X is equal to 0. Okay. And this equation, which has solution X not equal to 0, provided the determinant of A minus lambda I is actually equal to 0. Okay. And we get what we call the characteristic equation. And that is the determinant of A minus lambda I. And that looks like some alpha n lambda to the n plus alpha n minus 1 lambda to the n minus 1 all the way down to lambda down to alpha 1 lambda plus alpha naught is equal to 0. And here we get that. Okay, so you have to solve for lambda. Okay. Find the eigenvalue. So for example, if A is equal to 3, 2, minus 1, 0. Then A minus lambda I is equal to 3 minus lambda 2 minus 1 negative lambda, and then the determinant of A minus lambda I turns out to be minus lambda times 3 minus lambda plus 2, and that turns out to be to set that equal to 0, so you get lambda squared minus 3 lambda plus 2 is equal to 0. So that gives you lambda minus 2 times lambda minus 1 is equal to 0. So lambda is equal to 1 and 2. Okay. It's easy to find the eigenvectors of this system. Let's see. So for lambda equal to 1, you get A minus lambda I equals to 0 vector becomes 3 minus 1, which is 2, 2 minus 1 times some v1, v2 is equal to 0. And that implies that the vector v is 1 minus 1. So that's its eigenvector. And for lambda equal to 2, you get A minus lambda I equals 0, turns out to be 3 minus, so you get 1, 2, negative 1, negative 2 times v1, v2, and that equals 0. So that implies that v2 is equal to 2 minus 1. Okay, so those are, and you can do that for 3x3 systems, and so you guys are graduate students, you found eigenvectors for way more difficult problems than that. Sometimes you can have eigenvector multiplicities. That is the eigenvector. So for example, 215, 216. Whoops. Okay, so for example, where is my notes? 216, 217. Okay, I want 215, 214. Okay, here's another example. A is equal to 3 minus 2, 0. Negative 2, 3, 0. And 0, 0, 5. Now this is an easy one. I mean, ridiculously easy one to do. For this one, your eigenvalues, so your lambda turn out to be -1, 5, and 5. So for lambda equal to -1, you get v, its eigenvector, so lambda 1, its eigenvector v1. Turns out to be 1, 1, 0. And then for lambda 2, which is equal to lambda 3, which is equal to 5, you get v1, which is its first eigenvector, turns out to be -1, 1, 0. And its second eigenvector, v2, turns out to be 0, 0, 1. So you can talk about an eigenspace. So for lambda 1, its eigenspace is just the vector 1, 1, 0. And for lambda 2, its eigenspace is negative 1, 1, 0 and 0, 0, 1. There are things as eigenvector deficiencies. So like if lambda 2 only had one eigenvector, that would be an eigenvector deficiency. But when A, so there's a theorem. If A has a full rank of eigenvectors, then the eigenvectors are linearly independent. Okay. I should rephrase that though. I should rephrase that. Eigenvectors corresponding to, that's not what I want to say. Then eigenvectors, let me put that in. That's what I missed. Corresponding to distinct eigenvalues are linearly independent. That's what I was trying to say. I left out that the eigenvalues have to be distinct, and that's a big deal. Okay, so let's look at the power method. All right, so the power method okay, you want to act ugly today? Thank you. All right, so the power method. So this is a method, this is a method for computing the dominant eigenvalue and eigenvector. Now, why is that important? Do you remember there was a norm that used the eigenvector? So the spectral norm is the magnitude of the largest eigenvalue. So therefore, if you can find the dominant eigenvalue, you can actually find the spectral norm of a matrix, okay? So we're going to assume that we can take the absolute value of lambda 1 is bigger than the absolute value of lambda 2, which is bigger than the absolute value of lambda n. Okay, assuming again, this is greater than or equal to, and assuming again, A is an n by n matrix. Okay, all right, so the largest eigenvalue, that's the dominant, going to be lambda 1, and the dominant eigenvector is going to be V1. Okay, so definition. An eigenvector is said to be V, is said to be normalized if the coordinate of the largest magnitude is equal to unity. Okay, so that says i.e. the largest coordinate in V is equal to 1. Okay, so as you remember, we just did an example. Let me go back and call this example 1. And example 1, we got lambda, what V2 was 2 minus 1. This is example 2. So in example 1, we got V2 was 2 minus 1, I think, or 1 minus 2. I don't remember. What did we get? 2 minus 1. So therefore, it gets normalized and you get 1 negative a half. Okay. All right. So given V equal to V1, V2, Vn transpose. All right. We let C equal the max of 1 less than or equal to I less than or equal to N of the absolute value of Vi. And then V normalized we're just going to divide by that 1 over C, and then we get V1, V2, Vn, just like I did with that other vector. Okay, so suppose a matrix A has a dominant eigenvalue lambda. All right, and there is a unique eigenvector, unique normalized X or V corresponding to lambda. All right, so then we can then use the power method. Okay. Okay, so step one. We're going to start with a vector. V naught, well, a vector X naught, I apologize. And X naught, I'm just going to use 1, 1, 1, 1 transpose. Okay. So this is my initial approximation to V. Step two. Generate the sequence xk recursively using yk is a, whoops, is axk. Okay. Then xk plus 1 is equal to 1 over c k plus 1 times yk, and ck plus 1 is going to equal the largest magnitude of the coordinate with the largest magnitude of yk. So ck plus 1 is going to be the max 1 less than or equal to I less than or equal to n of the absolute value of yk at I. It's kind of hard to write. Let's see. Yk is the vector. I want the ith coordinate. Okay. So this is the coordinate of yk with the largest magnitude. Okay. So now you keep doing that. So step 3, what we will get is that V will be the limit as k goes to infinity of the xk's. So eventually they're going to start to look alike. And then lambda is the limit as k goes to infinity of the ck's. All right. So you'll have yk is going to be ck plus 1 times lambda k plus 1. That not right. This should be xk. Okay, so basically you continue the absolute value of ck plus 1 minus ck is less than epsilon, and the norm of xk plus 1 minus xk over okay. So here's an example. Okay, so we're going to use the power method. So here's A is the matrix 0, 11, negative 5, negative 2, 17, negative 7, negative 4, 26, negative 10. So that doesn't look like any fun. Okay, so the maximum eigenvector, so lambda max, maximum eigenvalue is actually equal 4, and its corresponding V is the vector 2/5, 3/5, 1. Okay, and again, that's normalized. Okay, so you let x naught one, 1, 1. Okay, so then y naught is equal to a x naught. So you're going to take the same matrix, okay, it's frozen. So we're going to take that matrix and multiply it by 1, 1, 1. And you end up with the matrix 6, 8, 12. Okay. So then x1, we're going to divide everything by 12. So we're going to get 1/2, 2/3, and 1. Okay. All right, so now y1 is going to be ax1. So we're going to take the matrix again. And multiply it this time by 1/2, 2/3, and 1. And this time we get 7/3, 10/3, 16/3. So now we're going to divide by 16/3. So here, the biggest one was 12. We divided by 12. Here, the biggest one is 16/3. So we're going to divide by 16/3. We're going to get x2. It's going to give me 7/16, 10/16, which is 5/8, and 1. Okay. We can keep doing this. And we get to y10, which is a times x10. And it turns out to be 1.600860 to 0.401095 and 4.001564. And then C11 is to divide by the biggest number. So that is the 4.001564. And when I do that, I get x11 turns out to be 0.400059 0.60039 and 1. Okay, which is approximately 2/5, 6/10, which is 3/5, and 1. Okay. So that's the power method. If I had time, I would derive it. We don't, so I am not going to derive it. The rate of convergence, let's talk about that. Okay. All right, so the rate of convergence This thing is of order lambda 2 over lambda 1 to the k. Let me go back a quick sec. So let's let UK all right, be the sequence of scalars all right, be the sequence of scalars which converge to lambda 1. Again, lambda 1 being the eigenvalue of largest magnitude. Okay, so we get the absolute value, and actually that is a mu, not u. So mu k minus lambda 1 is approximately a constant a times the absolute value of lambda 2 over lambda 1 to the k at any iterate. And the absolute value of mu to the k plus 1 minus lambda is approximately some constant a over lambda 2 over lambda 1 to the k plus 1. So you get the limit as k approaches infinity of the absolute value of mu k plus 1 minus lambda, needs to be lambda 1, divided by mu k minus lambda 1 is approximately lambda 2 over lambda 1 to the k, and that's less than 1. Okay. So the sequence mu k converges linearly to lambda 1. All right. And we didn't talk about it, but I told you to look at it. Aitken's procedure can be used to speed up the convergence. Okay. So what are the disadvantages of the power method? How much time do we have? Ooh, we run out of time, All right. Okay. First thing is, it's unknown at the onset. All right. If the matrix A has a dominant eigenvalue. Okay. Second thing, it's unknown how to choose X naught. And thirdly, the method depends on how fast the absolute value, well, lambda 2 over lambda 1 to the k goes to 0. Okay. So that's the difficulty. All right, so here's the algorithm. All right, so we need the input, and that is the matrix Aij. We need to know n. We need to know X naught, our guess. We need an epsilon tolerance. Okay. We also need to know Imax, which is the maximum number of iterations. Always put an Imax in there because you don't want your code to be going and it's calculating something over and over again, which is minus infinity, and it doesn't know what to do, but you haven't told it to stop at after 5 times. Okay. All right. So for k equals 0 up to Imax, we let yk equal a times xk. Now this is real easy in MATLAB. Then you can find c. Then you let c equal the max of yk. All right. If c is equal to 0, print that x is equal to your eigenvector. You don't have to go any further. And 0 is equal to your eigenvalue. And then stop. Okay, so if that doesn't happen, let error equal the max of xk minus 1 over c yk. All right. Then you let xk plus 1 equal 1 over c yk. If error is less than epsilon, then print c and x stop. And if that, you keep doing that to end. Okay, so that's the algorithm. Now, there's also the inverse power method. If A is invertible, then A inverse exists. There's a theorem if lambda equals 0 is an eigenvector, eigenvalue of A, then A is singular. The reason why that's important is the next theorem, and that's if A inverse exists, then if lambda is an eigenvalue of A, and 1 over lambda is an eigenvalue of A inverse. Okay. So for the inverse power method, okay, to find the smallest eigenvalue of a matrix A n by n, you find the largest eigenvalue of A inverse. Oh, let me say one other thing. The eigenvalues, the eigenvectors stay the same. Okay. So that's the inverse power method. All right. The last thing is Gershgorin's circle theorem. Gersch. Okay. So let A again and be an n by n matrix. All right. Let me write, let A be an element of M n by n. So that's the vector space of all n by n matrices. So we're going to define Ri is going to equal the circle in the complex plane with the center AII. Okay. And the radius that's going to be defined by the sum j equal 1 to n, j not equal to I, of the absolute value of Aij. So we're going to write Ri is going to equal the set of all z that's an element of complex numbers such that the absolute value or the modulus of z minus AII is less than or equal to the sum j equal 1 to n, j not equal to I, of the absolute value of Aij. So that is the radius, the circle, that's this circle. Okay. Then the eigenvalues of A are contained within what we're going to call R, which is the union of all these circles. Okay. So the union of any K of these circles that do not intersect the remaining n minus K circles must contain precisely K of the eigenvalues. So here's an example. So let's let A be the matrix 4, 1, 1, 0, 2, 1, -2, 0, 9. Okay. So A11 is 4, A12, nope, A22 is 2, and A33 is 9. Okay. So the first R11, sorry, R1 is the set of all Z that are complex such that the modulus of Z minus A11, which is 4, has to be less than or equal to the absolute value of 1 plus the absolute value of 1. All right. So that's the set of all Z that are complex such that Z minus 4 is less than or equal to 2. R2, set of all Z that are complex such that the modulus of Z minus 2 is less than or equal to 0 plus 1. So that's the set of all Z such that the modulus of Z minus 2 is less than 1 or equal to 1. And the last one is R3, set of all Z that are in C, modulus of Z minus 9 is less than or equal to the absolute value of minus 2 plus the absolute value of 0. That's the set of all Z in C such that the modulus of Z minus 9 is less than or equal to 2. Okay. So if I were to draw on the number line, and I'm going to change this for a moment just because I can. So that's too small. Okay. Okay, so all right, so here's 2. Here's 4. 5, 6, 7, 8, and here's 9. Okay, so now I need around 2, a circle of radius 1. Ooh, I'm hungry. Okay, and I need around 4, a circle of radius 2. And I need around 9, a circle of radius 2. So let's see if we can copy this. Okay, do what I want, copy. Okay. So as you can see, we have this intersection right here. So just in that small region right there, I know I have two eigenvalues. And then in here, I know there's one eigenvalue. So Gersh-Gorin's circle theorem can give you an idea of where your eigenvalues are. Okay. Let's see, we have 5 minutes. We talked about that. Talked about these. I do not have time to do the next topic. So I think I'm going to call this done. Hey, yep, I'm gonna call it done, a done semester. Okay, any questions?
Oh, like for the finals,